Vibration analysis. Time and frequency analysis technique Part 1. Our agenda in this time will talk about introduction, basic physics, single frequency, in phase, out of phase, and imbalance, single frequency with harmonics, and clipping and square wave. Vibration analysis. Time and frequency analysis technique. Introduction. There are 4 reasons regarding accurate diagnosis of problems in rotating machines requires a thorough understanding of the time domain signal and the frequency domain spectra. Reason number 1, the time signal is a plot of amplitude versus time. This signal contains all frequencies, harmonics, and subharmonics. The phase relationships of these frequencies are also contained in the signal. Pulses, amplitude modulation, frequency modulation, truncation, and distortion are also present. Reason number 2, the frequency spectra are plots of amplitude versus frequency. These spectra contain frequency, harmonics, subharmonics, and sum and difference frequencies. The fast Fourier transform, FFT, produces the frequency spectrum from the time signal, based on electronic physics. However, during the process, some information is lost. For example, phase, true amplitude of pulses, nature of the pulses, bandwidth, and the various forms of modulation are not easily identified in the frequency spectrum. Reason number 3, a mechanical machine may not generate a fundamental plus harmonics in the same way as in the electronic world. However, a rotating machine does generate relatively linear signals when a linear problem exists, such as imbalance. A machine can generate a distorted signal as a result of a nonlinear problem. This distorted signal is a composite signal, as would be obtained after various frequencies and harmonics are combined. Reason number 4, for the reasons 1, 2, and 3, various time signals can produce the same frequency spectrum. This explains why the time signal must be considered. Costly errors in diagnostics and loss of credibility could occur if the time signal is not analyzed. Before analyzing the time signal, an understanding of how frequencies add and subtract, and the effects of the phase relationships is required. It may be helpful to remember that multiplication is a series of additions, and division is a series of subtractions. This section explains the time signal in a non-mathematical way. However, extensive use of a computer and the signal analysis program or SAP are necessary to provide graphic representations of various signals and how they mix. The signal analysis program or SAP software performs the required mathematics. Vibration analysis. Time and frequency analysis technique. Basic physics. All things in the universe obey the basic laws of physics. Vibration signals from rotating machinery must obey these same basic laws of physics. This is why we can take data from either side of a motor and receive the same results. Some slight variations can occur in nonlinear systems because of transfer functions. In a pure linear system, data taken in different directions around a motor should be the same, except for phase. In the video vibration analysis introduction defined that a sine wave is the plot of a circle against time. All complete circles contain 360 degrees and all complete sine waves contain 360 degrees. The phase of a signal can be anything from 0 to 360 degrees, depending on the reference point. For example, in comparing a signal taken from the horizontal direction with a signal taken from the vertical direction, one signal should lag the other signal by 90 degrees. This is because the positions from horizontal to vertical are 90 degrees apart on the machine. This phase relationship should also apply to other data taken at various points around the machine. The time signal is continuous from start to stop of the machine. Concerning the phase of the fundamental frequency, the starting point happens purely by chance, depending on the exact instant of time when data collection is started. We can start taking data at any instant of time or location, and it does not make any difference. The reason for this is the phase relationship between the fundamental and other frequencies, or a once per revolution marker, will remain constant. These frequencies will add and subtract, depending on the phase relationship. When the signals are in phase, the amplitudes will add. This is why positive sidebands occur on some frequencies. When the signals are out of phase, they will subtract. This is why negative sidebands occur. This also explains how and why truncation occurs. Because of the above physics, a given frequency spectrum and time signal can take many forms, depending on the phase relationships of the various signals, including harmonics. In rotating machines, several different problems can generate the same frequency spectrum. For example, a machine that is loose can generate a fundamental and the second harmonic. A machine that has a bent shaft can also generate a fundamental and the second harmonic. The only way to determine which problem exists is to determine the phase relationship between the fundamental and the second harmonic. If these two signals are in phase, the shaft is bent. If the two signals are out of phase, the machine is loose. Currently, the only way to determine this phase relationship is with the time signal. The meanings of various phase relationships for specific problems are discussed in more detail in other chapters. Vibration analysis. Time and frequency analysis technique. Now we'll talk about the following single frequency. Number 1, single frequency. Number 2, single frequency minus 90 degrees phase shift. Number 3, single frequency 180 degrees phase shift. Number 4, two signals 180 degrees out of phase. Number 5, two signals equal in amplitude and in phase. Number 6, single frequency imbalance. A single frequency is often referred to as a discrete frequency and is the simplest form of frequency data. Figure 1 contains the time signal of a single frequency and the resulting frequency spectrum from the signal analysis program. The time period for each cycle is 0.01667 seconds and the signal is sinusoidal. Sinusoidal simply means the signal follows the sine function. Mathematically, the time signal is y equals to a multiplied by cos of 360 multiply f multiply t plus phase angle, where y stand for instantaneous value of the signal, a stand for the 0 to peak amplitude, theta stand for the phase angle, degrees, t stand for time variable, seconds, f stand for the frequency variable, hertz. The time signals for signal analysis program or SAP are based on the cosine function. The reason for using the cosine instead of the sine is because the starting point at time 0 of the fundamental is the highest point. The cosine is the same as the sine, except for a 90 degrees phase shift. Figure 1 is a cosine function with a peak amplitude of 1.0 engineering units or EU. In the real world, the signal can start at any point between 0 and 360 degrees. Figure 2 is a representation of a sine function with a peak amplitude of 1.0 engineering units or EU. Comparing this signal to the signal in Figure 1, a phase shift of minus 90 degrees is present. The signal in Figure 2 represents the sine wave with the phase starting at 0 degrees. The difference between the signals in Figure 1 and Figure 2 is the effective difference between taking data in the horizontal and vertical positions. The signals are 90 degrees out of phase. Comparing this signal to the signal in Figure 1, a phase shift of minus 90 degrees is present. The signal in Figure 2 represents the sine wave with the phase starting at 0 degrees. The signals are 90 degrees out of phase. Cosine is used for signal analysis program, SAP, because the real part of the fast Fourier transform or FFT is based on the cosine function. The following mathematical description of the fast Fourier transform or FFT is given for those readers interested in the mathematics used to break the complex waveforms down into the discrete frequencies. The fast Fourier transform, FFT, is based on cosine x, j sine x, where cosine x equals real component of signal, j equals imaginary variable, j squared 2 is equal to minus 1, sine x equals imaginary component of signal. When the time signal is processed by the fast Fourier transform or FFT, it is divided into the amplitudes and phases of the individual cosine and sine functions. When a spectrum is displayed, the plot is an amplitude plot of the frequencies. If a complex fast Fourier transform or FFT is performed, both the amplitude and phase are available, but only the amplitude is displayed. In the introduction, the frequency spectrum was said to lose the phase. In actuality, it may not be lost. It is just not listed or is discarded. Unless the phase is retained and viewed, the time domain signal must be used to identify phase relationships. To reconstruct the time signals from the frequency domain, a starting point must be selected. When time equals 0, the cosine starts at maximum amplitude and the sine starts at 0 amplitude. It is more consistent to start at the maximum amplitude of all signals, so the signals add at a time equal to 0. The signal in figure 3 starts at maximum negative amplitude. This is a cosine function with a 180 degrees phase shift. In rotating machinery, data taken from opposite sides of a motor should be the same, except the phases of the fundamental should be 180 degrees apart. This obeys all laws of physics. Amplitudes of signals in rotating machinery will add or subtract, depending on their phase relationships. The top grid in figure 4 contains two frequencies at 60 Hz which are 180 degrees out of phase. The time signal in the bottom grid has zero amplitude because the two signals are equal in amplitude, 180 degrees out of phase, and one signal cancels the other signal. This is the analytical proof. The empirical proof can be observed in balancing. Equipment is out of balance because one side is heavier than the other side. This generates a signal, as in figure 1. The equipment is balanced by placing a weight on the light side equal to the heavy place. This generates another signal 180 degrees out of phase, as in figure 3. If the two signals were equal in amplitude and 180 degrees out of phase, they would cancel, as in figure 4. In the real world, such perfection does not exist. However, it does prove that the amplitudes of out-of-phase signals subtract. The top grid in figure 5 contains two in-phase signals equal in amplitude. The top grid appears to contain only one signal. The signal in the bottom grid in figure 5 is the result of signal 1 plus signal 2, and the amplitude has doubled. The cases discussed in figure 4 and figure 5 prove that the amplitudes of frequencies can subtract when out of phase and add when in phase. This data also proves the overall vibration measured in most machines can be either over or understated. Therefore, phase must be accounted for to accurately identify the severity of a problem. This explains why amplitude trending is misleading. Figure 6 is an example of an imbalanced single frequency. The data was taken from a 3,600 RPM boiler feedwater pump that is out of balance. This example has some small differences from the theoretical single frequency. The real-world case is not a perfect signal and shows some effects of distortion. The distortion in the time signal may not be visible to the unaided eye, but it is present. The spectral line at 60 Hz is the frequency of the time signal. The low frequency noise and the harmonics of 60 Hz are caused by distortion. In this case, the frequencies at these levels are considered insignificant because they could be caused by very minor nonlinearity in the machine or some other source. Vibration analysis. Time and frequency analysis technique. Single frequency with harmonics. The second, third, fourth, etc. harmonics can be either in phase or out of phase with the fundamental. The phase relationships between the fundamental and the harmonics are valuable in diagnosing problems in rotating machines. Failure to understand and use the time signal and harmonic phase can result in diagnostic errors. The same physics that permit two signals to add and subtract apply to a single frequency with harmonics. A harmonic is some exact multiple of a discrete frequency. The discrete frequency, called the fundamental, is the first harmonic. The second frequency, which is 2 times the fundamental frequency, is the second harmonic. A single frequency without harmonics will have one positive going peak per time period, as indicated in figure 1. The number of positive going peaks in one time period of the fundamental frequency identifies the highest number of true harmonics. This is true for a single frequency with harmonics only and is true regardless of the phase relationships between the fundamental and the harmonics. The amplitudes of the fundamental and the harmonics determine the amplitudes of the positive going peaks. However, the phase relationships of the harmonics to the fundamental determine the locations of the positive going peaks in the signal. For example, the top grid in figure 7 contains a fundamental and second harmonic. The second harmonic is in phase with the fundamental and goes completely out of and back into phase with the fundamental once each time period of the fundamental. The bottom signal in figure 7 is the result of the top two signals adding and subtracting. It is important to note several points. Number 1 is the amplitude of the positive going composite signal is doubled because both signals are the same amplitude, and the positive going signals are added. And number 2 is the amplitude of the negative going composite signal is less because one cycle of the second harmonic is 180 degrees out of phase with the negative going portion of the fundamental. Number 3 is the second positive going peak is at the bottom of the fundamental, and the amplitude of the composite signal is 0. Once again, the reason for this is both signals are equal in amplitude, and they subtract. And number 4 is the composite signal is truncated on the bottom or negative side. The time period for each frequency is marked on each grid. The phase of the fundamental is changed 180 degrees in Figure 8. The two signals are still in phase because the harmonics are referenced with respect to the fundamental, as can be seen in the top grid. Both signals in Figure 7 start at the maximum value. In Figure 8, the fundamental starts at the maximum negative value, and the second harmonic starts at maximum positive value. It is important to note that the phase of the harmonic in reference to the fundamental is at the start of the cycle. In Figure 7 and Figure 8, the harmonic is in phase with the fundamental. The highest point of both signals occurs at the same point. At any other point in the cycle, the harmonic goes out of phase and back into phase with the fundamental. The net effect of the 180-degree phase shift is that the fundamental in the top grid and the composite signal in the bottom grid are shifted 180 degrees. The overall effect does not change the shape of the composite signal. The phase relationship between the fundamental and second harmonic is unchanged. In rotating equipment, the signals in Figure 7 and Figure 8 are the same result as could be obtained by taking data on opposite sides of a motor. That is, the fundamentals would be 180 degrees out of phase, but the second harmonics would still be in phase with the fundamentals. Again, this proves that data can be taken from either side of a machine without affecting the phase relationships of the harmonics. The top grid in Figure 9 contains a fundamental and a second harmonic. The second harmonic is 180 degrees out of phase with the fundamental. When this occurs, the second harmonic is in phase with the fundamental when both signals are maximum negative, and out of phase when the fundamental is maximum positive. This can be seen because the signals add when the fundamental is at maximum negative amplitude and subtract at maximum positive amplitude. The result is a higher negative amplitude in the composite signal in the bottom grid, and the two positive going peaks are at the top. The top grid contains both signals and displays how they go into and out of phase as they did previously. However, the second harmonic subtracts from the fundamental at the start of the fundamental cycle. Please note the composite signal still has two positive going peaks that identify the fundamental and second harmonic. However, both positive going peaks are at the top of the signal. This can only occur if the second harmonic is 180 degrees out of phase with the fundamental. Several points concerning amplitude must be made for Figure 9. Number 1 is, the zero-to-peak amplitude of the negative going peak below 0 is equal to the zero-to-peak amplitude of F1 F2. Number 2 is, the zero-to-peak amplitudes of each positive going peak are equal to the zero-to-peak amplitudes of F1 F2. Number 3 is, these amplitude relationships are true only for two signals equal in amplitude and 180 degrees out of phase. These phase and amplitude relationships hold true for linear systems. However, most real applications contain nonlinearities, called distortion. The distortion can appear in the signal as a phase shift in one or more of the harmonics. Distortion of the signal can also generate additional harmonics in the frequency domain which are not true harmonics of the signal. Therefore, the number of peaks in the time signal must be checked for true harmonic content. Continuing with phase relationships, the next step is to observe a phase shift of 90 degrees. Figure 10 and Figure 11 contain signals with a plus 90 and a minus 90 degree phase shift of the second harmonics, respectively. In Figure 10, the composite signal still has two peaks per cycle, denoting the second harmonic. However, instead of a discrete high and low peak, the lower peak is shifted to the left, on the downward slope of the signal. Figure 11 has the same uneven peaks, except the lower peak has shifted to the right and is on the upward slope of the signal. It can also be shown that any angle between 0 and 180 degrees can be approximated by looking at the various phase shifts. For example, a positive phase shift of the second harmonic will move the lower peak to the left. As the phase approaches 180 degrees, the lower peak will approach the same amplitude of the higher peak and the signal will look like the signal in Figure 9. In addition to phase shifts, the amplitudes can change. Figure 12 shows the second harmonic change to 1/2 the amplitude of the fundamental. The starting amplitude of the composite signal is still the sum of the two amplitudes, 1.0 engineering units 0.5 engineering units equals 1.5 engineering units. However, the lower peak is smaller and does not have a zero amplitude. The two signals do not cancel each other because the second harmonic only subtracts 1/2 of the fundamental amplitude when it is 180 degrees out of phase. After seeing the effect of changing amplitude in figure 12, one can identify the effect of changing the amplitudes in other ways. Changing amplitude only affects the amplitude of the composite peak. It does not affect the number of peaks or the phase relationship of the composite. The signals in figure 7 through figure 12 illustrate the effects of changing the phase and amplitude. With Signal Analysis Program or SAP, the amplitude, phase, and harmonic content can be identified, and these phase relationships between the fundamental and harmonics contain valuable diagnostic information. For example, if the spectra from a machine contain only a fundamental frequency generated by rotating speed and a second harmonic that is in phase with the fundamental, the shaft may be bent. If the second harmonic is out of phase with the fundamental, the machine may be loose. If the second harmonic of gear mesh frequency is out of phase with the fundamental, the gears have a backlash problem or are oscillating. If the second harmonic is in phase with the fundamental, the gears may be bottoming out. A good rule to remember is that if the source of the harmonic is tied to the source of the fundamental, such as a fixed, geared, or bolted coupling, the harmonic should be in phase. If the source of the harmonic is not tied to the source of the fundamental, the harmonic should be out of phase. This is also discussed in more detail later. The addition of a third harmonic will now be examined, along with the effects of changing the phase and amplitude. Changing the amplitude changes the amplitude of the individual peaks, as with two harmonics. Figure 13 contains a signal with three harmonics. 3 positive peaks per cycle are present, indicating the three harmonics. The amplitudes of the positive peaks above 0 are equal to frequency 1 add by frequency 2 add by frequency 3. So, 1.0 engineering units and 1.0 engineering units and 1.0 engineering units equals to 3.0 engineering units. The high peaks occur at the fundamental frequency of 60 Hz. The lower peaks occur at the third harmonic frequency of 180 Hz. The signal in figure 14 contains only the first and third harmonics. The negative portion of the signal is more pronounced because the second harmonic is not present to subtract out the third harmonic. In fact, one cycle of the third harmonic is in phase with the negative portion, causing the two signals to add. The amplitudes of the negative and positive portions are equal to frequency 1 add by frequency 3. So, 1.0 engineering units add by 0.5 engineering units equals 1.5 engineering units. When the first three harmonics are distinctive, misalignment is indicated. This fact was documented several years ago by VCI. However, until recently, the differences between the many time signals that can generate the same spectrum were not evaluated. These differences can now be explained because of the phase relationships of the harmonics. The phase relationships of the harmonics can significantly alter the time signal without affecting the frequency spectrum. There are an infinite number of phase and amplitude combinations possible. Figure 15 through Figure 20 show representative signals that have been identified on live data. For example, Figure 15 is a result of a misaligned, rigid coupling. Misalignment is indicated because of the distinct first three harmonics, which must be in phase because of the rigid coupling. If a rigid coupling is not used, the phase of the harmonics will change, depending on the coupling. If the coupling is rigid, it acts in a linear manner. If the coupling is loose or non-rigid, it will appear non-linear and out of phase. Figures 16 through 19 showing the single frequency with two phase-shifted harmonic. Figure 21 contains a spectrum from a main turbine generator. The time signal contains the basic features of the signal in Figure 20. 3 harmonics are present and the third harmonic is 180 degrees out of phase with the fundamental. Note the signal amplitude is less on the positive half than the negative half. This is a form of distortion called truncation. Truncation occurs when the machine is more flexible in one direction than in the other direction. The first three harmonics in the frequency spectrum are also distinctive. These spectral lines are the result of the three positive going peaks in the time signal. The low-level harmonics in the frequency spectrum are a result of the distortion in the time signal, and are not true harmonics. The first three harmonics are true harmonics in this spectrum. The time domain signal is necessary to verify which harmonics are true and which harmonics are caused by distortion. In this case, the distortion is caused by various non-linearities and is not required for analysis of this problem. Vibration analysis. Time and frequency analysis technique. Clipping in square wave. A signal is said to be clipped when a slight amount of the positive or negative signal is flattened, as in Figure 22. The upper signal is an undistorted time signal. The lower signal is clipped at the bottom. Figure 23 contains a time signal and a spectrum from a motor. The time signal is clipped. Such a signal can be generated when a machine goes against a stop in one direction and cannot move further in that direction for a small period of time. As the cycle continues, the machine moves away from the stop in a relatively linear manner. The signal is distorted because the time period for the negative and positive portion is not the same. Clipping is also a form of distortion. The frequency spectrum contains very little harmonic content, because in order for harmonic content to be generated, the signal distortion must be repeatable. In this case, the signal distortion is not repeatable. The non-repeatable distortion is noise. The skirts on either side of the 29.6 Hz spectral line, predominantly on the low side, contain the noise. The spectrum is up off / the baseline to the left of the spectral line, which indicates looseness or random motion. Now, in general, we are talking about square wave. A special case to note is a single frequency with only odd harmonics present, as in Figure 24. The harmonics tend to cancel each other out, except for one positive and one negative peak per time period of the fundamental. The peaks have an amplitude equal to the sum of all the amplitudes added together. A special case of odd harmonics is shown in Figure 25. Figure 25 has only odd harmonics, and every other odd harmonic is 180 degrees out of phase. The resultant signal is a square wave. The amplitudes correspond to the amplitude of the fundamental divided by the harmonic number. For example, the harmonic 1 has amplitude is 10 divided by 1 equal to 10, the harmonic 3 has amplitude is 10 divided by 3 equal to 3.333, the harmonic 5 has amplitude is 10 divided by 5 equal to 2, and would be the same for next further harmonic number. Note that the signal is not exactly square, but has ripples. This is due to the fact that a limited number of odd harmonics are contained in the signal. A true square wave contains all odd harmonics, which cannot be truly simulated on a computer as a sum of the cosine functions. It may appear impossible for a piece of equipment to generate a square wave, but it is possible to generate a signal with square wave features. This can occur in a motor if the motor has a loose mount. If the mounting bolts are loose, the motor will tend to move up and down. If the motor moves up and is stopped by the mounting bolt, and then moves down and is stopped by the motor support, a square wave can be generated. If clipping occurs on both the top and bottom of a signal and the clipping is significant, the result will resemble a square wave. Thank you.